So hey, my name is Nick Eberts. I'm a product manager on the GKE team. I work on platform engineering stuff. We've got a fun session today. I'm going to introduce Maciek here, and he's going to go over and tell you his job and all the great things that we're going to show you today. So,
thanks, Nick. So yes, my name is Maciek Rozacki. I'm a product manager along with Nick on the Google Kubernetes Engine team. You cannot imagine how happy we are to see you all. For those of you watching this on YouTube, this is a session that's happening on the last day of the conference, 8:30 a.m., right after the concert. We have a full room in here of hardcore platform engineers who want to learn how to build AI development and serving platforms. So together with Nick, we're going to show you how can you use GKE Google Kubernetes Engine, a variety of infrastructure capabilities around them, to run your own AI innovation platforms that help you build, train, and serve AI models. What we're going to be talking about can be applied also to a variety of other use cases, not only related to AI, like quant research, anything really that where you are first creating certain capabilities, insight, knowledge, whatever that will be in your case, offline without much of end user traffic, and then eventually you end up offering a product that's served into the big world. And yeah, we actually should have probably introduced ourselves as part of this slide. Let's then go and talk a little bit about platform engineering. So platform management, platform operations teams usually are trying to optimize four primary objectives that we see when we work with our customers and users. And those are quite contrary and difficult to achieve all together. One, everyone expects and needs a capability and set of software products that help them get started easily. And it's not only something that you do once. Nowadays, with the incredible innovations that are happening in the hardware space, it feels like whenever you move to a new fantastic hardware generation with the new accelerators, new network fabrics, it actually does feel like building your platform from scratch. So really the need for having capabilities that give you the easy start is something that is like a cyclical, recurring need that all of the platform teams have. The main reason why you do have these AI research platforms is actually to innovate. So everyone cares and wants about the velocity of innovation, the velocity of research. So how do you really power your users so that they can build and innovate as fast as possible and without any hurdles and problems? Platform teams are usually expected to, as their personal result, to achieve very high efficiency of resources utilization and make sure that the scientific output of the dollars that your company is spending is maximized from the hardware that was bought and invested into. And last but not least, these platforms usually operate at large scale, and that scale keeps growing and expanding on a variety of dimensions, not only computing power, but the scale dimensions associated with organizational complexity, diversity of workloads, number of services that only keep growing and expanding within the capabilities that you're building. And so, but first, let's say, usually teams are starting small, and even if it's another generation of your platforms, usually you would consider it small in the sense of it's going to be a platform that's usually serving one purpose, one objective. Let's say it's building the next foundational model that's going to revolutionize software engineering, and the entire team that's working on it is focused only on that one objective. That means that it makes a lot of space for taking certain design decisions that simplify the design of the platform, but this also creates a lot of pressure when it comes to how fast can you get started, how fast can you build your capabilities. What I mentioned though in here is that among things that are small, even on this initial stage, I would not say computing power is the small thing. Computing power very frequently, even for teams that are either startups that were just founded to build a new model, or some new departments that were created in a large enterprise to work on the sides on a new bet or a new capability and research behind it. They may upfront be starting with significant funding to buy a lot of servers, a lot of computing power, but still the research teams and the platform teams and the whole system layer is usually very simple, and the speed of quickly getting to the productive work is the primary objective that the team is trying to achieve. But then, as that team is successful, this brings lots of complexity. So if you build your first model and it's really successful, it's actually being used. Well, you have your production inference traffic or whatever is the activity that helps you actually capitalize on the investment into the model or the research that was done. You may be already working on a new model, or maybe 3 of them with a variance of multimodalities or various sizes, and you may still be iterating on the old one, maintaining it, making sure it's well aligned. So you start to have a variety of types of workloads. Your research organization is going to grow. So first, maybe it just might be multiple people. Later, it might actually turn into a full organization. It might start a certain structure. So it might have certain dynamics that are typical for structured organizations. And on top of it, as your platform is expanding in your computing power, very frequently the new additions, new extensions of computing power into your systems will involve new regions, new hardware models, new storage types. So the complexity of the infrastructure abstractions, not abstractions really, concepts and products that are being used in your platform, that complexity is also going to be growing. So with this success and the growth of complexity across all of these dimensions, usually there is a tax that the platform management teams need to pay. Either there is just loads of more work to do, and I don't know how it is in your companies, but very few CFOs really like to have conversations about increasing staffing levels of each of teams. So this is always a challenge, that you have more work and it's more demanding, while at the same time it's very hard to grow the team as you're getting more and more work. It is also very difficult, as complexity in your systems grows, to maintain high levels of efficiency of the infrastructure that is being used in your platform. And last but not least, usually with size and complexity, velocity goes down. And it's difficult to make sure that you don't try to compensate, for example, for problems with efficiency of your systems or with the amount of work that the platform team has, that the velocity and research, the innovation pace of your company actually starts to go down. That's the main reason why actually usually such a platform is going to exist, is so that actually the innovation can be happening fast. So what we believe is that Kubernetes can be a system that is central to such platforms, that allows you to scale across all of the challenging dimensions of complexity of your platforms, and mitigate these consequences and be able to start easily, simply, small, so that there is not much hurdle and overhead when you're creating your first environment, and then allow you to gradually evolve the platform and grow over time as your business and your capabilities are growing and evolving, without the necessity to pay the taxes, to pay for the consequences of the success, let's say, that you had. And the mental model that we've devised together with Nick for how it's good to reason about the layering of the systems and how to structure the platform is in these 3 layers that you see here on the screen. So first and foremost, you're going to have a set of capabilities, modules, add-ons of varied complexity that are exposing endpoints to your users. These are going to be the front ends, the endpoints that researchers use to do their jobs. And there's going to be a variety of abstractions and types of capabilities in here, from very simple core Kubernetes products like Kubernetes job, or a more complicated job set for them to simply build the YAML file that deploys the workload into the cluster, up to a very complicated capabilities of multi-layer schedulers, where you have a Kubernetes cluster and on top of it you actually step yet another cluster based on Storm technology or Ray, and then on top of it you have further even endpoints and front ends for your users. So all of that plethora of various capabilities that are helping your research teams innovate fast. On the bottom layer, maybe Hilard go, this is the space where there is fabulous innovation happening at the moment in the industry, with the various new hardware generations, new infrastructure constructs being built, new, even more powerful network storage capabilities. all that are very diverse, very vendor-specific, and very usually also complex and difficult to use. So here Kubernetes gives you the necessary endpoints and standardized wrappers, APIs, that help expose high performance and differentiated hardware into other layers in the stack so that they can easily plug and leverage them. And then the middle layer is the one where Kubernetes orchestration happens, where Kubernetes and the add-ons that you put into the platform is capable of connecting the capabilities that are running and exposing functionalities to the end user with the underlying hardware, and is able to broker and analyze and help manage a variety of activities that are happening both in the various front ends and in the complex underlying infrastructure, in a way that like teams that are evolving and building the various capabilities across the platform don't really need to know each other. They don't need to be that familiar with what the other team is doing, as long as they conform to certain open source standards of Kubernetes to do that. And so let's take a closer look at some of them, and you're going to get actually a deeper dive into these, during the demo, to see how they actually work. The first one that we wanted to highlight is MultiKueue. This is a capability that we've built together with the open source community to help you perform multi-cluster batch job dispatching across a fleet of clusters. So in a scenario where either you have your machines located in a variety of regions, maybe even providers, some are on premises, or you simply want to fragment them perhaps by security profiles. A very common case is that you still want to expose a single endpoint through which job admission and scheduling is going to happen. So MultiKueue is a capability that allows you to either broadcast workloads across your fleet or have it assign workloads to clusters with a specific logic that you configure and set up. And then when a workload lands on an individual cluster, a single cluster level queue kicks in. This is a batch add-on to Kubernetes that we founded and then evolved together with the open source community that allows you to express both the organizational structures and needs of your research teams. So essentially allows you to set up quotas, borrowing limits, how resources are, it allows you to decide which job should run, which should wait to be allowed to run. And that simple action requires a sophisticated and complicated API, because if you really think about what it's doing, it's a software system that's deciding that in your company, in your enterprise, a workload of person A is more important for the success of this company than that workload run by team person B, and it's doing it automatically all the time. So this is a very important decision. It has to model the organization dynamics, politics, how the budgets are structured and all of that, and translate it into policies that are automated through software that's running on the cluster. Secondly, what it's doing, as it's a scheduler, it's also performing the necessary optimizations to your workload to properly leverage the structure of the underlying infrastructure that's in the data center. That actually I'm going to show maybe in a second in more detail. So the way that this works, it's an admission controller that evaluates the configuration based on the quota management needs, the needs for the workload, like gang scheduling, the topology of our scheduling, so scheduling the workload in a way that it's aware of the structure of the data center and how servers are connected to one another. And based on that, decides which workloads should run, which not. Workloads that should not run, they sit suspended without any pods created, just the workload resource, and they are waiting for queue to unsuspend them, allow them to run. Queue also has integrations with our APIs in Google Cloud. The most important one is Dynamic Workload Scheduler, Flex Mode, that allows you to ask and wait for VMs that are more scarce, in particular large accelerators, so that we have a model where even if you do not have a reservation and the resources are not available in the standard on-demand fashion, you can still ask for them and wait for them to be provisioned with Dynamic Workload Scheduler. And this dynamic model of provisioning is brokered and wrapped in its complexity by queue. And now when you go from a cluster level, into a workload level, a different set of problems kick in. And in particular, what we see on these platforms is a special category of workloads that we call hero jobs. And among hero jobs, we'd even say that the most important ones are pre-training workloads. Very frequently, a single hero workload is going to consume 80% of all of your computing power. And they go up to that levels of scale. And the most important thing that you're after when you're evaluating how your platform is supporting that workload is what we call good put. So it's essentially the fraction of time that the workload was working productively and using the available hardware to its maximum potential. And to help reason about this metric, we are recommending to have it divided into 3 subcomponents, with scheduling good put being a metric that tells you for what fraction of time the workload had actually all the resources that it needs, particularly important in gang schedule workload where it's all or nothing. So this reflects the percent of time when the workload had everything that it needs to start running. Then the runtime good put metric is a metric that tells you for what percent of the time when the workload had the resources that it's running, it was doing something productive. So as an example of something that is bad put and not productive, it could be, for example, taking a checkpoint, taking a snapshot of the work that is happening. It's not really moving your work, right? It's actual risk mitigation. Or after a failure of a server, it's about the time that it's needed to recover from a failure and then catch up with all of the processing that you may have missed since the last checkpoint was taken. So these pieces then contribute to bad put within the runtime good put metric. The last, but also important metric within this equation is program good put, which tells you how effectively the programs that you're running are actually using the theoretical maximal computing power of the chip. Between these 3, this one is mostly impacted by how your researchers have built the scripts, the code that they are executing, and how effectively the frameworks that you're leveraging are built, while the first 2 components in particular are heavily dependent on the quality of how you've built the platform and how you set up the scheduling the orchestration layer. So on the next slide, I'm going to show you a couple of capabilities that you should be on the lookout for when designing your platform that allow you to optimize especially the first 2 parts of the good put metric. One important one is the multi-tier checkpointing feature, which gives you a simple API to automate a more complex and sophisticated way of taking checkpoints. Instead of simply saving them to a GCS bucket, multi-tier checkpointing allows you to save the checkpoints also in operational memory on your host, in the local storage of the VM that's processing, and also distribute those checkpoints on nearby VMs that are running around. So then, the checkpointing operation, especially for very large models, is much faster because the process of pushing the checkpoint to Google Cloud Storage is actually done asynchronously. And secondly, depending on the size of the failure that perhaps your workload experienced, but most likely the checkpoints are actually going to be available on nearby machines whenever you need to recover one particular VM. So then the recovery process is actually going to be much faster than in normal conditions. Second important capability I'd like to highlight to you that is that is available as a private feature that you need to ask for through a support ticket, but we are able to give you a configuration of the control plane that optimizes the cluster for scheduling throughput. And you can relatively easily achieve 300 pods a second of scheduling throughput for a very fast recovery process if you need to fully restart your workload, for example, and you want to do it in seconds ideally. This metric is particularly sensitive to also how you've designed your workload. So if you actually build the workload spec in a way that is very oriented on achieving high throughput, we've seen the highest characteristics of even 1,000 pods a second in terms of scheduling throughput on a single cluster. Third capability worth highlighting is automation of managing hot spare machines. So essentially, if you are running a very large workload, let's say 80% of your total capacity, you will keep the remaining 20% as a buffer in case you have any failures, so that you can quickly swap it and make sure the big 80% job still continues running. So then, in simple scenarios, job set workload controller allows you to automate that process. If you want to, in a more complicated scenario where especially you'd like some low priority workloads to be running and doing something on that spare capacity while the big job is running, then Kueue has the capabilities to allow you to let in small preemptible workloads to run on your spare capacity set on the side and quickly swap the machines into the cluster if necessary. Last but not least is the most sophisticated capability in here of elastic training. That is a capability built into the frameworks that are running on your cluster, the one that are used to execute your workload. The one that I wanted to highlight to you in here is Pathways on Google Cloud. That is a JAX backend based on internal innovations from our internal AI teams that allows you to run a workload at a certain scale, and if it experiences a failure, it briefly pauses and then restarts on a smaller set of machines until the repair process happens, then pauses again, extends the size of the workload, and proceeds running on a larger scale. This way, during the recovery process, the workload is still productive and moving forward, and that's one of the core capabilities that allows large model training to really achieve good puts that are getting really close to 100% and are in the upper 90% numbers. Now, when you go into the hardware layers and how this whole stack is integrated and is making sure with the core infrastructure capabilities, I wanted to highlight a few very important, two very important features that you need to be on the lookout when designing your platforms. One is topology over scheduling. Among the components that I've shown currently is baked into Kueue and the job set that allows you to express the needs of a workload to run with pods in a certain proximity, in a certain distance from one another, expressed usually in the number of hops it needs to do through switches in the data center. This allows you to run workloads that are sensitive to network latencies and performance between hosts so that they can scale more and run faster. But when you go deeper and now more from macro to micro scale, sometimes you may want to not divide the data center and understand that, but actually divide the machine and slice it into pieces and components. And the dynamic resource allocation is an open source capability that we've worked on together with the community that allows you to describe workloads needs when it comes to how the machine should be sliced, with a most common probably example of running workloads in a way that they understand the NUMA topology structure of the node, so that like your pod gets all of the resources on a certain portion of the motherboard where the graphics card and the network card is connected to the same CPU socket on which also the CPU processing is happening. And then on the front-end level, we wanted to highlight again that as long as your front-end capabilities and what you're exposing to your users are conforming to certain standards that we've devised with the open source community when it comes to using the right workload controllers like job set, leader worker set, that they do integrate with Kueue, then you can run a lot of things on your cluster. They don't need to be too aware of what's happening below or next to them. So you can run things like highly complicated and sophisticated Slurm cluster next to another Ray cluster on the same machine, combine it also with a Spark cluster and something bespoke that you've built to be running on your platform, connect tracking and profiling tools that are going to be giving you metrics and diagnostic information from those tools, and they are going to understand what's happening in the other capabilities. You can run various AI orchestration and work experiment management tools like XManager, MLflow, Kubeflow, and other. and they all are not going to step on each other. They are going to be connected, and they will be able to broker negotiations for access to resources. And last but not least, you will also be able to set capacity for prototyping and innovation and evaluation work, like working with notebooks, IDEs, and other tools that your researchers may use that are maybe of small scale, but very frequently also very unpredictable and abusive, I would say, in the way that they can be dangerous, so they also need to be well set up so that a researcher does not do something silly or mistaken while running still on production hardware. So you still get the capabilities to combine all of that in the front ends. Out of these, I wanted to quickly just highlight two new ones that we're launching new support for. So one is Xmanager. This is Google's used to be Google's internal experiment management platform. Now we're externalizing it, refreshing the GitHub repo that is published on the web, that allows you to deploy your own experiment management and tracking platform that helps researchers trigger experiments and collaborate on them. And this is a capability where whenever former Googler leaves Google and then starts a startup and wants to work with Google Cloud on building their own AI lab or research team, this is the most frequently asked for capability that they would like us to offer, that helps the research teams be more productive. Currently private preview, so you need to contact us to get access to it, but it's coming also. We didn't manage to do it before next, but shortly it's also coming to be simply published as a GitHub project that you can deploy on your own without our assistance. Then the second capability that we're launching right now, and this one was fully rolled out right before next, is a result of our collaboration with SkedMD, now acquired by NVIDIA, to deploy their Slurm operator that was created to help teams deploy Slurm clusters on top of Kubernetes. This is a capability especially sought after by those customers who hire researchers that have a supercomputing background, that come from HPC research centers, and they really love the fantastic ecosystem of research tools that Slurm comes with its over 2 decades of development on supercomputers. While at the same time, these teams do want to run other workloads where Kubernetes is the best tool for that. They want very tight integration with cloud resources. And Slurm operator add-on on GKE allows you to simply ask us to create an add-on in your cluster, and then through a custom resource that you deploy on the cluster, you are able to get a configured Slurm cluster with a data plane, control plane, logging nodes that your researchers will be able to use and access all of the hardware on that the GKE is managing. Last but not least, on this presentation, we just wanted to highlight that all of this research, all of this innovation has to end with serving something to your users. So then this is going to be the inference stack. And here we primarily want, since there is a lot of talks through this conference that dive deep into how this stack runs, here we primarily would like to just highlight to you that the gateway, inference gateway, LLMD, and all of these capabilities, they were built in collaboration with the teams that were working also on the more batch and backend research capabilities in a way that this is fully capable of coexisting with the other workloads. You can use MultiKueue, you can use Queue while on clusters that are also serving production traffic for inference, and you will be able to set up the necessary policies so that the resources can be assigned and moving dynamically between them. And maybe to best actually see it, I would invite Nick to show you this in a demo.
Hey, good job, man. Thank you.
Thank you, thank you.
All right, just bear with me for a second while I actually log into my computer. I was told this would be awkward, and it is not. Or maybe it is, I don't know. Okay, so how are y'all doing? You having a good conference? Yeah? Okay, cool. So Maciek went through a lot of things, and what I like to do, I'm a product manager, but I'm also an engineer at heart, and so I like to actually see how to put all these things together and build kind of prototypes out of them. So what you're looking at is a terminal UI. So let's hear it for, 2007. So terminal UIs are making a comeback. And this terminal UI is showing you some live action that's going on in a fleet of clusters that I have. So I have 3 clusters. I have 2 workload clusters, one in east and then one in west. And I have a management cluster. And that management cluster has MultiKueue installed on it and multi-cluster gateway. Anyone, show of hands, anyone using fleets today? Okay, cool. So it requires fleets. That's GKE's cluster list, right? And access to these kind of multi-cluster capabilities through fleets also works with open source cluster profile, which is the analogous feature in the community. So when I'm using fleets, I'm actually replicating the metadata about the members and the labels that are on it to a central cluster in the form of a cluster profile. And then MultiKueue is consuming that list. So we've done kind of the plumbing to pipe metadata about cluster memberships into the management cluster. So multi-cluster gateway is running right now. You can see I have, I've got VLLM, I think it's Llama 3.1 running in each of these clusters. So there's 2 instances running in each cluster, and the HPA on is set to max at 6 replicas and min at 2. And the point of this whole demo is we're just going to try to use GPUs as efficiently as possible. I think my running tab right now is like, I probably shouldn't say it out loud, but these are real GPUs. This is live. So let's kick off the demo. I'm just going to run this script. And okay, so the first thing it's doing is it's just kind of showing you that we're using those 2 GPUs in each cluster for the inferencing servers. The inferencing servers are set up in the same priority system that MultiKueue is using. And so I have 3 types of workloads we're going to show today. One of them are inferencing, right, which is it's the middle of the road priority. Then we've got low priority experiments and high priority pre-training jobs. And so the first thing we'll do now is schedule one of those high priority jobs. This is gang scheduling and topology aware scheduling is sort of all in one step. You can see that the pre-training job got submitted. It's a job set of 6 different pods, each requiring 1 GPU. And it has been pushed out to the east cluster. And there was no problem right there because I had 6 GPUs available. It just scheduled. So that job set was posted to MultiKueue. MultiKueue ran some logic and said, hey, where can I go run this? Found the place to run it, and now it's running, right? The next thing I'm going to do is throw 40 low priority jobs at MultiKueue. And these low priority jobs each require 1 GPU. And you can see the queue depth of MultiKueue building up on the bottom. So it's gonna start processing these jobs. Each job takes approximately a minute. So you'll see it draw down the queue as I'm standing up here babbling. But what it's really showing you is that it's finding GPUs, spare GPUs, like in my fleet, and scheduling those jobs and trying to drain the work. So everything's happy right now. We've sort of brought no chaos to the situation, but that's not really fun. So let's see what happens when we throw a significant amount of load at the inference servers that are running. So I'm starting up a Python script that is going to send a pile of requests at the multi-cluster gateway endpoint. One thing I want to actually call out is that this is all within a multi-cluster gateway, which is essentially a controller that is configuring a Google Cloud Load Balancer, right? And that Google Cloud Load Balancer has an internal IP. So can we all just like take a minute to acknowledge how awesome that is? I've got an internal IP distributing traffic to 2 different clusters in 2 different regions. I'm not using DNS. Yeah. So that was underwhelming, but thank you for that. Yeah. And so traffic is getting routed to the region that's closest to the client, the Python load script right now. So it's going to the East Coast, and you can see that it's starting to fill up. Now, the other thing I'm doing with multi-cluster gateway is I'm routing on a custom metric. That custom metric is KV cache utilization. I've got it kind of set low. You probably want to get more than 60% out of your KV cache utilization, but I wanted to make this demo kind of work, right? So when the average KV cache utilization hits above 60% in the primary region, that traffic is then going to start failing over and spilling over to the secondary. You see it already happen, and it's enough load to actually start to push everything over. Now, the HPA in the primary region can't scale out because it's got that high priority pre-training job, right? So it's stuck. It's requesting, you could see, if you look at the HPA section, you see it's requesting more, but it's not going to get them because of the whole priority system, right? But on the West Coast, the inferencing workloads are of a higher priority than the experiments, and you probably already happened. You'll start to see experiments get evicted once the HPA on the West tries to scale out to meet the new demand of spiking traffic, right? So now traffic's going there. You see the HPA is trying to go for 5 replicas, and it already evicted 1 experiment. And right now, the reason why this part of the demo is a little bit slower is because I'm waiting for pods to come up, and if anyone is running VLLM and starting up inferencing servers, you know that it can take some time to pull down all of the weights. I am using image streaming, so the image is happening pretty quick, but it's the weights that are taking a little while. One thing I couldn't wire into this demo that I really wanted to was pod snapshotting. Pod snapshotting will take this down to 20 seconds from several minutes, because you can snapshot the weights and build that into streamlining, starting up that container on the cluster as it's scaling out. So thoroughly stalled, I think, as long as I can. How are we on time? Oh, we got 10 minutes. So again, that pod is coming up. The HPA is scaling out. There it goes. So now we just HPA'd. We've got a third inferencing server now running in the West. Traffic is going to continue to get distributed to it. And then here's the fourth. And one thing I also want to call out that's happening, so I'm using multi-cluster inference gateway. It's not just a multi-cluster gateway, it's a multi-cluster inference gateway. So it is doing like prefix-aware routing. So it's trying to get me to containers, inferencing servers that already have the context that I need. The other thing that's happening is there's a feature of multi-cluster, or of just inference gateway called flow control. And what flow control allows you to do, you can kind of set fairness of requests, right? So you can have quality of service in the requests that come through. If you pass a header in, then you can actually prefer a certain type of inference over another. So if you had a freemium tier and like a premium tier kind of thing, you could do that in the request header now and just use endpoint picker and flow control. And the other thing cool about inference gateway is that they did put a proxy in this situation, right? So there's a proxy called the endpoint picker that has to run with your inference server. And what this allows you to do, one added benefit of this is if you're willing to HPA to 0, and you're running an alpha server, so we have to get HPA to 0 out of alpha, but that's going to come soon. But if you're willing to scale to 0, you can actually have your HPA scale your inference server in your secondary and tertiary regions to 0. But the biggest problem with scale to 0 is you need something to receive the first request to say, hey, I need a replica. Endpoint picker is now that proxy if you want it to be. So we can get that first request and then fire up an HPA from 0 to 1. Historically, you would do that with Quota or Knative or some, hand-rolled proxy. So all that's cool. You can see now that the load has calmed down a little bit. I now have 5 replicas in the West. And the next thing that I'm going to do is drop another bomb on the system. I'm going to schedule another high-priority pre-training job. So it's submitting, and when I submit this pre-training job, it's going to find a home for it, and since it's the highest priority, it'll evict. You can see it already preempted an experiment. It's preempted some of those inference servers that I had running. And so I scheduled this, went through MultiKueue. MultiKueue looked at all of the workloads that are running in my fleet. I wrote a custom dispatcher to help it decide how and when it should evict, and it pretty much, it kind of runs on cruise control as long as you program that dispatcher to kind of use the logic that you would prefer when it's making decisions on contention for resources, right? Okay, So that job got scheduled. I'm still running. I backed off the load test, so traffic is gone now. And that is it. That is my whole demo, and I guess we have 5 minutes left. I also want to say, I'm going to switch back over to the slides, yeah. Okay, so I am not going to talk through these. These are awful. There's this one, there's that one, and that one. These are all, I just put them in the deck so that if you can download these slides later and you can go kind of take a look at the architecture and get a good idea of how you might want to put this together. Let's see. So that's it. So I think the TLDR here is, you definitely, if you're in this space and you're building a platform, or you're even if you're starting up and you're running experiments and you're starting something up, like you have these options to start small and expand bigger. And if you take just a little bit of time up front, you can set yourself up to have like minimal tech debt down the line by just acknowledging that maybe your needs will break out beyond just one single cluster. It's likely that's going to happen over time. Yeah, and we have a discussion group. Oh, no, that's not embedded. We have a discussion group. What time is the discussion group? Yeah, it's like 12:30. So if you want to come into that discussion group and have like a more detailed conversation about this kind of stuff, we're happy to do it.